All right, and welcome back to next video of homework 2 for transport phenomena 1. Okay, today we're going to be exploring the concept behind a rotometer. And a rotometer is a inexpensive device that's commonly installed along nitrogen lines, air lines, or otherwise some kind of fluid line to measure the volumetric flow rate of said fluid. And the way it measures that is measuring how far up does the ball go up in the meter. Okay. And I have a diagram shown here where lowercase d is the diameter of the ball, uppercase d is the diameter of the tube, which by the way is slightly bigger than the diameter of the ball, such that there is a very small gap here and here. Here. And this ball is lifted up some height because of the pressure differential, right? Because the fluid is flowing through. Okay. And in other words, what we're trying to find today is a function for height as a function of, I misspoke. What we're trying to find today is volumetric flow rate, Q, as a function of height here, okay? And we're going to reach that by two means. One, a force balance, and two, the idea of Bernoulli's equation, okay? And let's start with the force balance, okay? We know we have Fg, and we have FB directed upwards. And this FB is smaller than FG. I drew that deliberately because the for a rotometer to work, the density of the ball must be less than the density of the fluid. Okay? We also have a pressure force directed upwards and a pressure force directed downwards. Okay? And these pressure forces directed upwards is, generated by the fluid at position 1. And likewise, for the pressure force directed downwards. So let's go off and write our expressions. Okay, so FB, buoyant force. How is buoyant force represented? Rho Vg, right? So FB is equal to the density of the fluid displaced multiplied by the volume of the ball. Let's do lowercase b here. Volume of the ball multiplied by g. And Fg is equal to mg. Okay? And what do you notice about mass? Do you know that mass can be represented by by volume multiplied by density, right? So let's go off and do that because you notice that you can factor that out later. So volume of the ball multiplied by density of the ball equals multiplied by g. So what do we have? We can factor out volume of the ball multiplied by g, and let's see, Fg, so density of the ball minus density of the fluid equals what? Equals pressure force at 1 minus pressure force at 3. And you're gonna want to relate this to pressure somehow. So how do you know that pressure force? You know that pressure force is what? Pressure multiplied by area, right? And you also know that pressure force is always directed perpendicular to the sphere or the surface of contact. So you might think, oh man, I'm gonna have to do an integral with a sphere now. And that's not going to be the case here, because you recall from homework 1 of this class, Transport Phenomena 1, that you can represent the effective area of the pressure force, because the horizontal components all cancel each other out, leaving only the vertical components to generate a force. In other words, the cross-sectional area of the widest point of the sphere is the effective area of contact. So you can call F1, okay, we can call F1 is equal to P1 multiplied by the area of a circle in terms of diameter is pi d squared over 4, right? So we can go off and say F3 is equal to P3 pi d squared over 4. Okay? And now what? So we can plug that in here, right? And again, factor out what you can. So this is equal to pi d squared over 4 of P1 minus P3, okay? You notice that the volume of the ball can be represented in terms of diameter as well. And this is a different formula. This formula is, I believe, pi d cubed over 6. Okay, so that can cancel out. We have, that's gone, that's gone, pi's gone, pi is gone. We have 2 over 3 d g rho. Oh, I should probably write that a line down actually. 2 over 3 dg quantity rho b minus rho f. Equals P1 minus P3. Almost done here. Oh, not done with the whole thing, but almost to a good checkpoint. And that is, now we have to talk about the idea of a, what do you call it? A sudden expansion, right? And you recall that from the last video just before this, that a sudden expansion means that there is no frictional heating, which was going to eventually help us with Bernoulli's equation here. But now we have to identify, is this a sudden expansion? So let's look at the continuity equation here. The volumetric flow rate is equal to, let's do area 1, velocity 1 is equal to, actually that's not going to help us. Let's do area 3, velocity 3 is equal to area 2, velocity 2. All right? You notice that, well, this is really small. It's an extremely small gap. So the area of 2 is very, very, very small, much smaller than area at 3. What does that mean? It means that you're gonna go from a small little cross-sectional area like that to a great big one like that for a very small change in height, d height. So maybe I should make more sense to rotate that. Well, I'm not gonna rotate that, but for a very small change in d height. So because of that, we can then classify the movement from position 2 to position 3 as a sudden expansion. In other words, a sudden expansion, you'll recall that a sudden expansion means that there is no pressure recovery. Therefore, the pressure at 2 is equal to pressure at 3. Pressure at 2 is equal to pressure at 3. So we can then go down here and rewrite this as P1 minus P2. That's a very good expression that we're going to use later on. Okay? All right. So now that we have our force balance done, we can go ahead and apply our Bernoulli's equation to this particular situation. Okay? And Bernoulli's equation is like so. Honestly, you should have this memorized at this point. Plus the velocity term, plus the height term. Let's do height here. Oops. Height equals, and we're going to say frictional heating is 0 to make this calculation feasible. We're going to make a lot of things go to 0 in today's calculation. Now, speaking of, you notice that the rotometer is actually really small. It's very small. And because it's very small, the relative change in height is not that large compared to the other values. Therefore, this change in height is negligible. Okay? And so what should we go off and do now? By the way, you might notice what the goal might be here. We have this expression is equal to that, and we have the opposite of that. So eventually something's gonna happen there. Okay, so let's go off and see what we can do here. We have V1 and V2, and let's relate V1 and V2 by the continuity expression, where we say that the volumetric flow rate is equal to A2 V2 equals A1 V1. And let's replace V1 here, because we wanna take a look at position 2, that infinitesimally, well, not infinitesimally, that very small gap. Okay, so we say that A1, or rather V1 is equal to A2 2 over A1 V2. Let's go off and plug that in. We then have V2 squared minus A2 over A1 V2 squared all over 2. You can then factor out a V2 squared and a 2. So V2 squared over 2 is, minus, or rather multiplied by 1 minus A2 over A1 squared. So that's our velocity term in Bernoulli's equation. But we have a detail here. What did we say earlier about A2 and A1? That A2 is so much smaller than A1 that it's a sudden expansion, right? Or in this case, it is a sudden expansion. So it's A2, the ratio is already extremely small, and you're squaring it too, which makes it even smaller. So this actually goes to 0. So our velocity expression then simply becomes V2 squared over 2. Okay, so now what? Recall that we're looking for volumetric flow rate. Okay, so volume by the continuity equation again. The volumetric flow rate is equal to what? The volumetric flow rate is equal to, let's do A2 multiplied by V2. So let's look for an expression for V2. So this equals 0. We have P2 minus P1 over rho F, right? Oh, plus. Okay. All right. I ran out of room in the last page, so I went ahead and moved us to a new page and grabbed our relevant mathematical expressions. So let's again. We tell ourselves that the volumetric flow rate, this is what we're solving for, right? The volumetric flow rate is equal to A2 multiplied by V2, where we see, hey, we have V2 right here. Why don't we isolate that? And we go ahead and do it. And it looks like this. So let's do well, actually, if we, that's where I was getting confused. If we subtract that to the other side, then this P2 minus P1 becomes P1 minus P2. There's where you see that we match, right? Over rho F, okay? Multiplied by 2, and it's taking the square root of. Okay, that is V2. Now what? We then find that we should plug in this expression. Okay, so then V2 equals radical. Let's do 2 times 2 is 4, so 4 over 3 diameter G times rho of density of the ball minus density of the fluid all over all over density of the fluid. Okay, so there's our expression for V2. Expression for volume at position 2, right? So now we want to find volumetric flow rate. And you might look at this and say, hey, I don't see height. Don't see a height yet. So how the heck do we make a function of volumetric flow rate as a function of height? Well, you see, when I drew the earlier diagram, I purposely misled you. In reality, there is a very small taper. Well, such that the diameter of the bottom of the taper is equal to the diameter of the ball, because you don't want your ball to fall straight through your meter. And this taper is a function of height. Okay? Function of height. Such that, well, the big D, the diameter of the tube, is going to equal height multiplied by some constant, because it's a function of height, right? At the same time, you should treat this as a coordinate plane, right? So that the x-intercept is going to be D. So D, little d plus mh. Okay, little d plus mh is equal to big D. So the reason why this is important is if you take a look top down, we want to now find an expression for area, right? Area of our, what do you call it? Our flow. And the gap, the area of the gap, right? So you take a look at you look down your rotometer and you see something like this, where we are interested, that's not perfect, but we're interested in this area between here, which is the difference between big D and little d, right? Uppercase D and lowercase d. And the area is going to be what? It's going to be how should I do this? Let's do A2 is equal to pi big D squared over 4 minus pi little d squared over 4, right? So you can factor out your constants. You have pi over 4 of big D squared minus little d squared. Okay? Where big D is this function here. So if you go off and square that, you get d squared plus 2 d mh plus m squared h squared. And again, this taper is extremely small. So because of this m squared h squared term, this is being squared, this you can say goes to 0. You get rid of that. Okay, remember that. It's a rather small detail and it's easy to forget. Okay, so you plug this term into big D squared. So we have A2 equals pi over 4 diameter of the sphere plus 2d mh minus diameter of the sphere squared. You see that d squared cancels. So now you have an expression for a squared equals pi over 4 2d mh. I realized that my h looked a lot awful like a b there, so let's fix that. dmh. Therefore, a2 equals pi over 2 dmh. Now, that was a lot of algebra. Now we can write an expression for volumetric flow rate, where volumetric flow rate is equal to pi over 2 dmh multiplied by this guy right here. Hold on. There we go. Okay. So paste. There we go. And you notice that you can pull that 4 out and make it a 2. And then that cancels. That cancels. Right? So you are left with Q is equal to pi dm radical dg rho b minus rho f over rho f. I'll put the 3 down there, and let's put the h all the way to the right. Because I do that deliberately, this is now our expression for volumetric flow rate. I do that deliberately because pi is a constant, diameter of the sphere is a constant. M is going to be the slope of the taper. Everything here are constants, so you can represent all this as some arbitrary constant. Okay, then multiply by h. Therefore, this is now our function for volumetric flow rate as a function of height of the rotometer, of the ball in the rotometer. And this will conclude part 2 of homework 2 for transport phenomena 1.